In this video, we're going to wrap up our discussion about regression and residuals, at least for this chapter. So we've been talking for a little while now about regression lines and their residuals because, no line of best fit is going to make 100% correct predictions all the time. It's just not how it works, not in the real world anyway. So how well do those regression lines really fit our data? So let's go back to our well-loved, well-used Ford F-150 data. And let's say I have this point right here, right? Its residual is negative 4765. That would mean that the predicted value of that car, of what that car would sell for, actually was almost $5,000 higher than the actual sale price of that particular vehicle. It's going to happen. Now, what if we took all of the residual values, which in fact, here are all of them, which you can actually find with your calculator. Go back to that last video. It'll show you how to do that. And we can take that knowledge of the actual residual measurement, positive, negative, whatever you want, and we can calculate the average or typical prediction error. And of course, that typical prediction error has a name and a letter associated with it, or a variable. So that's the standard deviation of residuals. So it shouldn't surprise you that standard deviation comes out here, right? Because we've learned before that a standard deviation is about how far a particular data point is from the mean or the average. So an outlier, let's say, or something that is not exactly on average. So that would make sense that residuals have that same kind of idea. Now, it looks a lot like standard deviation, but it just has to do with residuals instead of the mean or the average. So it measures the size of a typical residual, that is S, measures the typical distance between the actual Y value, so like the actual sale price of that Ford F-150, and the predicted Y value, or that $5,000 more sticker price that you'll probably see if you go looking for used cars, if you haven't already. Here's the equation and what it looks like in math speak. So how you calculate S, or the standard deviation of residuals, which is the average error that you're going to have when you have a line of best fit. So you take the sum of all the squared residuals. So you square all the residuals, you add them up, you divide by however many values you have, you subtract 2, you find that fraction, you take the square root. And there is your S, or your standard deviation of residuals. And in fact, when you do that for the Ford F-150 data, there was no truck Bitmoji. I don't know why. This is the best I got. The average error, or the average S value, the standard deviation of residuals, the average of that is about $5,740, which makes sense for that example. There's another numerical value that helps us figure out how well our lines of best fit, or our regression lines, actually fit our data. And that's something that we call the coefficient of determination. I don't know why I said it like that, but it felt right. So that is also called R squared. You've probably seen it when you do calculations like linear regressions, and you've seen R before. R, remember, is what we call correlation. So correlation measures the direction and strength of the association. So we're taking that idea of squaring residuals and squaring correlation to figure out, well, how well is this thing actually modeling our data? So instead of talking about the average value of Y, or your response variable, and in terms of our Ford F-150s, that's going to be our price, we're going to look at the least squares regression line. So what you're looking at here are two different graphs. This one is the sum of squared residuals, and that's if you use the mean price. So that's if you added up all the prices of those 16 F-150s and you averaged them out and you said, all right, let's do the residuals to the mean, or the average. This one is our line of best fit, right? Our regression, or least squares regression line. And so that's if you take all the residuals and you square them and you add them up. You actually get a smaller number when you add up all the residual squares to the line of best fit compared to the residual squares to the mean. So what's happening in these two graphs is that we have information about the residuals from the average and the residuals to the regression line, or the line of best fit. They're both dealing with residuals that are squared and added up together. This is the value for when you do it to the mean, and this is the value when you do it to the line of best fit. Both are useful in calculating R squared, or our coefficient of determination. We'll talk about what that means in a second. So essentially, you take the number from the mean, average, sum, thing, and then you subtract the one from the line of best fit. And then you divide it by the one from the mean, because that one's always bigger, FYI. And you get a number that is roughly a percentage. So if I get 0.66, that means it's 66%. R squared is always a percentage. So what does that mean in this used car world? It means that the sum of squared residuals has been reduced by 66%. That means that about 66% of the variability in the price, so, right, like the difference, am I paying $5,000 more for this truck or not? So the variability is represented in that line of best fit. So 66% is not terrible. That would mean that the other 34% accounts for other things that are not being attributed to this data, like the age of the car, the color of the car, the condition of the vehicle, where the vehicle is from the person who wants to buy it, etc. So that's what we do with R squared. That's why we use it, and that's what we do with it. So let's talk about the relationship between that S, that standard deviation of residuals, and our R squared, or the coefficient of determination. First up, both are calculated from the sum of residuals and measure how well the line fits the data. The standard deviation of residuals, or our S, that reports the size of a typical prediction error in the same units as your Y value, or your response variable. The coefficient of determination, R squared, doesn't have units, right? It's a percentage. You know what's coming. Let's do an example. This one is about grabbing candy, again. So scatter plot here represents the relationship between hand span in centimeters and the amount of candies, starburst, that you can grab, or that were grabbed in this particular experiment. So our regression line is this equation here, which is this blue line right there. And when we use our calculator or any kind of statistical software, it gives us our S value of 4.03 and our R squared of 0.697. So we're going to interpret the value of both. Here's how both shake out. So S, remember, has to do with standard deviation. Like, how far away is our prediction from the actuality? How good is our prediction? So we would say the actual number of starburst grabbed is typically about 4 candies away from the number predicted by the least squares regression line, where X is hand span. And then R squared talks about a percentage, right? So that means that 69.7% of the variability in the number of starburst grabbed is accounted for by the regression line, where X, again, is hand span. So S talks about the value of how far away your prediction is from the data that you've collected. And then R squared has to do with the percent of variability that is contained in that least squared regression line. Next, I want to show you how to interpret computer regression output. So you're very well aware that there are more computer programs and statistical software than your calculator, although you should also know how to use your calculator. And they will output information. They will calculate all the things. They've been programmed to do that. But when you get the output, you have to be able to read it. Otherwise, it's pretty much useless to you. So using 2 different types of really popular software, one is Minitab and one is JMP, I want to show you how you can read computer output without necessarily doing it yourself. So, compared to when you want to do a linear regression on your calculator, each of these and other computer printouts essentially give you the slope and the y-intercept of those regression lines. So the slope would be, for example, miles driven in that used Ford F-150. So it would always be the miles driven here. And then they call it the constant for the y-intercept, which is right there. And then over here at JMP, it's still going to be miles driven for the slope, and then it literally says intercept there. And obviously, some of these computer programs either truncate or round the numbers, so it's really up to you how many decimal points you want to include. Use your best judgment depending on the variables. Also, we want to look for our S value. So literally, this one calls it S, standard deviation of the residuals. Over here, it's called root mean square error. So you just got to look for that. And then R squared is usually called R square, or this R dash SQ, or R square. R squared is usually the really clear one to find. So, using that information, let's do an example. This example is called using feet to predict height. I'm sure you've heard that one before. So the problem says a random sample of 15 high school students were selected from the U.S. Census at School database. The foot length in centimeters and height also in centimeters of each student in the sample were recorded. Here's the scatter plot with the least squares regression line added, that green line there, a residual plot, and some computer output. So take a moment, look at these, and then we'll move on to the questions. First up, we're asked, is a line an appropriate model to use for these data? Explain how you know. Now, I would hope that you have enough information to answer this question, but I would say yes. Now, this line is great, looks great for this data. It's not super duper close, but that's okay. We've got residuals. And then I'm looking at the residual plot over here. Now, it doesn't make any funny U shapes, so I would say yeah. A more formal way to say, yeah, yeah, sure, is that the scatter plot shows a linear association and the residual plot has no obvious leftover curved patterns. It looks kind of random, like random dots, which is a good thing. So a line is an appropriate model to use for these data. Next up, we're going to find the correlation. So remember, correlation is just R. So I'm going to look for anything that has an R or R squared value, and I find it right here. So I'm going to take this R squared value, turn it into a decimal, take the square root, and we'll find our correlation. 48.6 as a percent is 0.486 as a decimal. Take the square root of that, and I get the correlation, or my R, is 0.697. Now, something to keep in mind here is that if you have the R squared value, think about R. Whenever you take the square root of something, you have to consider, well, is it positive or negative? The way you look for that is you look for the slope. And remember, that is going to be given as whatever the variable, the units, whatever we're looking for there. And so this one is foot length. And the foot length here is positive, so that means my R value is positive. Now, if the slope was negative, your R value would also be negative. So just be aware of that. Next, we're being asked to write the equation of our least squares regression that describes the relationship between foot length and height. So we're going to use foot length. That is our slope of our equation, so our m times x. And then our constant, remember, now that's going to be our y-intercept. Now let's write this in terms of our variables. So we start with height, so that is our output, our response variable. So height has that hat on it, where that would normally be the y-hat. Now you can put the slope times x first and then add the y-intercept, like mx plus b, but typically it's b plus mx. Just however you want to do it, it's okay. So this would be our y-intercept first. That's going to be that 103.41. Because there are two zeros after it, I leave them off. You could include them. And then we're going to add our slope. So that is our foot length. So 2.7469, that slope, that average there. 2.7469 times our x, which is foot length. So this thing in red and purple here is our equation. last question is, by about how much do the actual heights typically vary from the values predicted by the least squares regression line with x equals foot length? So when you're asked how much something varies, that should spring to mind standard deviation. So that's going to be our S value here. So we could say that the S value there is about 7.95. Again, you can include all those digits if you want to. So what that means is the actual heights typically vary about almost 8 centimeters from the values predicted by the regression line, where x equals foot length. Now, before we end this video, I want to share with you 3 pieces of correlation and regression wisdom. First up is correlation and regression lines describe only linear relationships. That's something we've talked about. That's something you've probably picked up. Only works for linear relationships. How do you determine that? I know it's a little tedious, but depending on the technology you use, always plot your data first. Now, here are 4 graphs that are apparently very, very famous, developed by a famous statistician. And basically, what's amazing about it is that all of them have the same correlation value and regression equation. But obviously, not all of them would be best represented by a line of best fit. Certainly not this one, certainly not this one, and maybe this one? Probably this one. So make sure you always plot it and use your eyeballs to figure out, all right, is this a line? Is this the best use of a linear regression model? Plot your data first. Second piece of wisdom I have for you is that correlation and least squares regression lines are not resistant. They're not resistant to outliers, first and foremost. So the best way to kind of look into the influence of outliers is to do regression calculations with and without the outlier and see how much the results differ. So if you take a look at this scatter plot here, we've got the age at first word in months and some test score, small children. That's what they're measuring here. And so we've got this outlier here of child 19 and child 18. And if you were to make a residual plot, you'd see that child 19 goes all the way up here and child 18 is all the way over here. So what would happen to our lines of best fit and our correlation values if we removed each of those kids from the data? Now, it may not seem that significant, but this green line is the same green line here, including both kids. Then this blue line here is without child 18, and you can look at their values here. And then this red line is without child 19, which you can look at here. Essentially, all of this information is telling us that with or without outliers, correlation and our regression lines are heavily influenced, so hence not resistant. So beware of your outliers. And also take into consideration what they do to your data. And last but not least, we've talked about this before, but it bears repeating. Association does not imply causation. A couple of things about that. So a strong association between 2 variables is not quite enough to draw conclusions about cause and effect. Sometimes an observed variable really does reflect cause and effect, but beware that associations may be explained by other variables. So, for example, a study once found that people with 2 cars live longer than people with only 1 car. Owning 3 cars is even better, according to that data, and so on. So there's a substantial positive association between number of cars and the length of your life. But can we lengthen our lives by buying more cars? No. So you can have an association between 2 things, but that doesn't mean that owning more cars is going to make you live longer. That's not a cause and effect. And lastly, it only makes sense to talk about correlation between 2 quantitative variables. Again, we've heard this, but if one or more variables is categorical, then we refer to that association between them instead of a correlation. And if you're unsure, just use the word association. It'll save you some trouble. And that's going to do it for this video. I'm going to find me a big giant floor piano, like in the movie Big, and play myself out. Thanks for watching.